Sure. All right, I think I'm recording. All right. So last module, the challenge was kind of data processing and learning pivot tables. Did you guys enjoy pivot tables? They're a little different, but if you have a giant data set, they're a really quick way to pull out metrics, and it can be way bigger than the data set we had. So if you're ever in a position you've got this giant Excel table and you need to get some data out, then pivot tables might be a good way to do it. We're going to focus on a different challenge in this module, because I know you like challenges. Oh, I think I just need to click here. There we go. So there's going to be actually very little data processing. I will do most of it for you, but the challenge is going to be interpreting your data, and we're going to go beyond mean reaction time. We're actually going to do a distribution analysis. So that's, you saw a bit in the readings, and we'll go through that today with a few examples so you can see what a distribution analysis looks like. Distribution analysis, we're going to be using ex-Gaussian distribution functions. We'll go through what those are. In your presentations, you don't need to explain what a distribution analysis is. So just like in your presentations, you didn't explain what mean reaction time is, mostly. We're going to assume some of this knowledge going forward, and we'll circle back to that so that hopefully it makes sense. Oops. The other interesting thing about this module is we're going to do a new experiment. So previously what we did is we tried to replicate other famous experiments, but we actually have an applied research question, and we're going to run an experiment. We're going to see what the answer is. So if we think about reaction time, here we're really trying to zoom in on pressing the button, maybe not properly to scale. But what happens in this task, we think about time along the x-axis here. We get a go signal, so maybe it's a stimulus, a visual stimulus. And then what happens is you go through information processing, and eventually your movement starts. So I tried to animate just kind of the start of the movement. It was hard in PowerPoint just to do a tiny bit. But you imagine as soon as we start to move, that's movement initiation. Now, eventually, so this interval, that's our reaction time from the go signal to movement initiation. Eventually, on that button press, you will press the button down and it will actuate. The voltage signal will change. And that is the end of your movement, or movement termination. And the interval from movement initiation to movement termination is movement time. And we have a name for reaction time plus movement time. It's total response time. So what you might be seeing from this is, well, in those other studies we've done, we talked about your reaction time, and that wasn't technically correct. We were technically measuring total response time, the time from the go signal until movement initiates and until movement terminates, or more precisely, when the button actuates. But there's a difference between starting your movement and the time until the button actually clicks, or the voltage signal changes. And yes, it's short. It doesn't take long for you to press a button, but we have maybe unnecessarily added a small movement time onto our reaction time values. So we call it reaction time, but we were not technically correct, although this is very common in research. Now, why is this common for button pressing research? Well, two reasons. The movement time is typically short. So how long does it take you to press a button? I'm not sure exactly, but definitely less than 100 milliseconds. It might be only 10 to 20 milliseconds, depending on the individual and the type of button. So that's why we're not too concerned that we added movement time on to our reaction time. And also the idea is that, well, there's probably very little variability to that. So how long it takes you to press the button is probably about the same, regardless of whether it's compatible or incompatible, or your right hand or your left hand. So if we're always overestimating reaction time by a small constant about, it's not a big deal. So what we've been calling reaction time has been overestimated by a small movement time component related to how long does it take you to press that button. So that's my kind of argument for, not a big deal. Now here's my argument for it is a big deal. So what's science? So as scientists, we should measure dependent variables like reaction time as accurately as possible. And sometimes button press studies, they will say, well, we're not measuring reaction time. They will say we're measuring total response time to be more precise. And that's definitely one approach. The other thing, what we're going to try to do here is we're going to try to find a button that's a more accurate measurement of reaction time. So we're going to compare two different push buttons. One are the ones we've used in the last couple of modules, those small white ones. And we're also going to look at some large yellow buttons. They're not that much bigger, but relatively larger, and they're yellow instead of white. So our assumption here is that the button with the shorter total response time is more accurate at estimating reaction time. So if the total response time is shorter, the reaction time should be the same between the two buttons. What's different is the movement time. And well, here, let's look at it on this graph. Oh, okay, so this is our little competition. This is our experiment. It's the big yellow button. So these are the new ones you've maybe seen in the lab, but these are the ones you've actually used before, the small white ones. So let's say we have two buttons. Let's say we have a blue button, and let's say we have a yellow button. And the idea is when you do this experiment, so yes, your reaction time is slightly different on each trial, but if we do a bunch of trials, we should get a pretty good estimate of your mean reaction time. So we're going to assume that those should be the same with both buttons. The difference is the movement time. How long does it take you to actuate that specific button? And in this case, the blue button has a longer movement time than the orange button. Or in other words, what we'd be measuring is total response time. This one would be slightly longer, this one would be slightly shorter. So we can conclude that the orange button is better because the amount it overestimates reaction time is smaller than the blue button. So we're going to be looking at these two buttons. We're going to be measuring total response time. We'll call it reaction time as we have in the previous modules. But whichever one has the shorter reaction time is the more accurate button. So the experiment, it's going to be I was going to say simple experiment, but it's not simple reaction time, it's two choice, which is a relatively simple experiment. So there's a joke in there about simple and two choice reaction time. I once referred to simple reaction time as one choice reaction time, and one of my advisors thought that was hilarious. In later years, more recently, there was a book on reaction time, and I think they actually called simple one choice, and I always meant to send it back to that my advisor and say, yeah, look, I'm not crazy, but it's probably a bit crazy. So we're going to do two choice reaction time. We got two conditions. You're either using the big yellow buttons or the small white buttons. And I forget the exact counterbalance, but let's say participant 1 starts with this one and then does this one, and participant 2 would do the opposite order, and so on to counterbalance, starting condition or maybe fatigue throughout the experiment. In each condition, so fairly standard, we've got 16 practice trials before, but you'll notice we bumped up the number of test trials. And that's because we're going to do a reaction time distribution analysis. And for that, we need, the standard is at least 100 good trials. So it will recycle bad trials. We've got a few extra in case we lose a few along the way. Yes, Keith.
Didn't the paper you sent us say you needed thousands of trials to do a distribution?
You need thousands of trials to accurately measure skew or skewness.
Oh,
yeah. So that's, yeah, we can't do that. Well, we could try to do that, I guess. But yeah, the next best plan, rather than measuring skewness, is to do a distribution analysis, which you can get away with 100.
but
There's actually a backup to that where you can probably get away with 40. That's for another year, I suppose. So this is an actual experiment being run in the lab right now. We've collected a few participants already. So we have I guess there's a few of us on the research team. So 2 students in this class, myself, Chelsea is an undergraduate in kinesiology, And Kobe is an undergraduate out of the Honors College who's doing a kind of an independent study within the Honors College. So a few things about this. It's going to be a little formal, more formal than before. So it won't be a, drop in and test yourself. It will be one of the members of the research team will be there to test you. There'll be a consent form. It'll just be a little more official because this is an actual study. Because it is an actual study, I cannot force you to do it. So if you'd like to volunteer to do it, that would be great. If you don't, what I can do is I can give you some de-identified data, not from someone in this class, but some of my undergraduate students are doing this. These undergraduate students are doing de-identify their data and give that to you instead if you don't want to volunteer. I guess the benefit to volunteering is that you'll get firsthand experience over what these two sets of buttons feel like. And then when you're interpreting the data, you'll be interpreting your own data, which is hopefully more meaningful. So this is a follow-up to an experiment that I've written up, but we're still working on having accepted. And in this study, we looked at least 13 different ways. I don't think all 13 are in here. Some of them didn't make the final cut of measuring reaction time. And you can see here, this is an overall score for the button. And these scores, the theoretical limit was 1 to 0. So 1 would be the worst, 0 would be the best at all 4 criteria. So you can see a button is actually doing pretty well. And a button is simple. And it's been used for, well, a few decades in psychology research. And it seems like it actually has worth. There are a few measures that are better. So this is getting into, let's see, kinematics. We have some kinetic measures. So this would be, position, velocity, acceleration is kinematics. Kinetics is force and yank. So there's yank, there's yank. So it's performing pretty well, which was a bit of a surprise because in a lot of motor behavior studies, we really emphasize kinematic measures without necessarily having a justification to say that they are better than a button. Now, we measured 4 characteristics of each measure to get this overall score, and the button performed really well on three out of 4 of them. And the one it didn't perform very well on is here, and it's reaction time, which I guess really should be total response time. And here, the lower the score, the better. So the position extrapolation method, which we don't need to worry about understanding, but it has a giant overestimation of reaction time. So some of this would be reaction time, and then like all of this is movement time being added on. So you can see that's a huge overestimation. Down here at the best end, we've got yank extrapolation, manual velocity, so either kinetics or kinematics, and we're talking about this is more than 100 milliseconds difference between the best and the worst. So it makes a difference. And here's our poor button. It is not doing very well on this score. It is, it's third from the end. And this is what you see a lot of people saying, oh, buttons, they're a huge overestimation of reaction time. That's true. So then they say, you shouldn't use them. And then my comment would be, well, although they're not good at reaction time, the other 3 things about them are actually good. So the goal is, well, can we look at a different buttons, so small white versus large yellow, and find one that maybe has a smaller overestimation of reaction time? And if so, then maybe a button would be really good at 3 measures and would be good at this 4th measure instead of being bad. And maybe it could be with a better reaction time, maybe would have the best overall score. So the hypothesis here is that one of the buttons will have a shorter total response time, and that button would be a more accurate estimate of reaction time. Now, what is different about these buttons besides that one is small and one is big and one is white and one is yellow? Well, we do have the technical specifications of these buttons, but I don't want to share them with you because I don't want to bias your performance. When you do this, you will feel that they are different, and that's okay. You know, they are different, and participants can tell that. But I don't want to bias anyone with an expectation of which one might be better. So, you know, if you volunteer, come in, give it a try, and then from your data, everyone will look at their individual data to see whether one button was faster than the other one for them. So any questions so far about the experiment? So for the second half of the presentation, we're going to talk about how to do a reaction time distribution analysis. And so this is really, you know, going beyond mean reaction time. Previously, we just said this was mean reaction time in this condition versus this condition. We're going to go deeper than that with the distribution analysis. It might sound a little scary, but instead of mean, we're going to get 3 values. So, you know, it's not a huge difference, but we're going to go from mean reaction time to 3 values that represent reaction time. One is a mean, one is a standard deviation, and then a third is a rate parameter. So that's a bit new for us. So probably before too long, you'll get an email about providing course feedback, and I would be happy if you have any thoughts to share about the class. It includes, you know, the standard kind of multiple choice, Likert scale questions, and then there's an opportunity for comments and anything you'd like to add, positive, negative, or neutral about the class. I would appreciate. This class gets taught every 2 years, and so it's a while between each cycle. But from the last time I taught it, which actually was 4 years ago, because there was a term where we skipped it because they pulled me in to teach stats. Anyways, I've changed it a lot since then based on feedback from the students and my experience of what I thought went well and didn't go well. So feel free to let me know what you do and don't like. I know it won't benefit you, but it will benefit the next cohort, and hopefully you had a better experience in this class than the cohort, you know, 4 years ago. Yes.
Do you remember what you changed?
Sure. Yeah. So 4 years ago, the course was assignment based, so we didn't have presentations, and we used MATLAB. We did a lot of coding, and the idea was to build up our MATLAB skills to be able to analyze data in reaction time experiments. So we talked about how to collect data, and we got very technical about sample frequency, things like that. So that was our first module. And then what we did at each week, we extended our analysis technique. So we started with, okay, how do we analyze one trial? And instead of where we had, in the Excel table, we got the data, we went to the raw data where you saw voltage signals changing. We had to figure out how to pull out those values in MATLAB for one trial. And then we did, okay, well, can we do all trials in one condition? And then can we do all the trials for one participant across several conditions? And this, okay, now how do we analyze data for all participants? And then once we had that, we moved into statistics. So how do we analyze data? We started with a t-test, and then a one-way ANOVA, and then a factorial ANOVA. And yes, students did not like it. They said, I don't want to use MATLAB. They said, I don't want it. This is not a stats course. Why am I using stats? And they said, I really want to know more about motor control theory. And to that one, I said, do you? But anyways, but I can appreciate MATLAB programming was not right for the class. It was a bigger class back then. There were over 20 of us. We had several football players. That was when, so Sandy can maybe attest to this, interdisciplinary students, we used to have lots of them. And they were free to register. And now you have to get permission from the professor to register. So before, we had some football players. So Sandy is a wonderful student. Please don't, think I'm saying otherwise. But we had a lot of students who would take our kinesiology classes who were just wanting to compete as athletes, and most of them failed, didn't even try. And anyways, it was a different time. Okay, so let's look at reaction time distribution analysis. And when we have a symmetrical distribution, and maybe the most famous symmetrical distribution is the normal distribution. And it's called the normal distribution because we see it in a lot of measurements. So if we measure height, we get a nice normal distribution. I call it normal because it's kind of the most common one we see. The other name for the normal distribution is the Gaussian distribution, and it's named in honor of Gauss or Gauss. I'm not quite sure how. A mathematician who kind of discovered the normal distribution. So posthumously, it's often referred to as the Gaussian distribution, and we're going to see that more today because we're going to look at the ex-Gaussian distribution, which is a version of the Gaussian distribution. So if we have a symmetrical distribution like the Gaussian distribution, the mean, median, and mode are all the same. They're all this middle value. And to properly describe this, all we need is one of these measurements and a measure of the variability. And the most common would be the standard deviation or the variance. So with these two things, we can describe that data. And we've been looking at mean reaction time. We could have, in our experiments, also looked at the standard deviation of reaction time. Now, the challenge is that lots of distributions are not normal. Reaction time, one of them has a positive skew. And when we have a positive skew, the mean, median, and mode no longer line up. They get stretched out. So it kind of now matters which one we report if it's a skewed distribution. And the other thing is, to describe this fully, we need one of those three measures of the mode. Of the average. Those are all measures of the average. We need a standard deviation. And then we also need the skewness. So how much is this tail pulled this way? That's the skew or skewness. And there are also, of course, distributions that are negatively skewed, but reaction time is positively skewed. So we'll stick with this shape. So if we want to do a distribution analysis on reaction time, we can't just do mean and standard deviation. We really should do mean, standard deviation, and skewness. So here's an example of reaction time data. So last time I presented, I mentioned that I tried doing the Simon task 4 times to get a bunch of data to hopefully make it look a little more like an X. And it wasn't great, and it wasn't great for your data either. But I went back and I pulled out all my compatible trials. And I think there's 256 of them, and I made a histogram. And what you can see is a positively skewed distribution. So it's, if it were just this, then it would be fairly normal shape. But we have this positive skew to it where there's a few trials that are a lot longer than all the other ones. And I can pull out the measures for it. So the mean is 417. Standard deviation is 113, and the skewness is 1.44. And I'm trying to remember with skewness if 1 means no skew. I forget. We're not going to use skewness, so you don't need to worry too much about it. Now notice that the majority of trials kind of make a somewhat normal distribution. And then out here in this skewed tail, we have a minority of trials. Now, why is reaction time positively skewed? Well, one logic to it is you can only be so fast on a reaction time trial. There's a lower limit. It's probably not 0 unless you anticipate, but let's say 100 milliseconds is the fastest you can be, but you can be infinitely slow. So, maybe a trial happens, you're a bit distracted, and you respond after 2 seconds. That would be a very slow trial. That would be one of those minority of trials way out here. Now, we don't have anything ridiculous technically you could respond after an hour, but that's why they suggest we see this shape, because you'd only be so fast, but every once in a while there's a trial that takes a bit longer, and that's going to positively skew your distribution. And we see this over and over with reaction time. I think I'd be surprised if you collected reaction time and you didn't find a positively skewed distribution. Okay, so the challenge with measuring mean, standard deviation, and skewness is skewness. So we can reliably measure reaction time and standard deviation. We can do that with 10, 20 trials easily. We cannot reliably measure skewness. And skewness, to measure reliably, requires thousands of trials, and participants don't typically want to do thousands of trials. And you probably couldn't do that all at once. You'd have to do several sessions, and it would be kind of ridiculous if I said, okay, time to do Simon effect. You know, you're going to do 5,000 trials. And even with thousands of trials, skewness is very sensitive to outliers. So if you had any times you were distracted with a really slow trial, that would potentially be a problem for measuring skewness. So although we can measure skewness, and I put a value up here, with one last trial or one more trial, this value is going to change a lot. So we cannot reliably measure it. So what we're going to do instead is a distribution analysis where we say, okay, you know, what is the shape that we have? And reaction time is well described by an ex-Gaussian distribution. We'll see that next. And then we're going to say, okay, well, what are the parameters of the ex-Gaussian distribution? And we can describe it with three variables. So it's a bit of a workaround to get past this problem with measuring skewness, which we can't do reliably with our type of data. Okay, so what is the ex-Gaussian distribution function? Well, the name ex-Gaussian is short for the exponentially modified Gaussian distribution function. So this is a normal distribution function, the one we know and love, and an exponential function, we're basically adding them together. And the math is literally take the Gaussian distribution, add an exponential distribution, and that gives you the ex-Gaussian distribution function. And this is what it looks like. So here is a normal distribution function. It has a mean of 308 and a standard deviation of 30.2. So we could use any normal distribution function. We're going to add this to an exponential function. And often when you think of an exponential function, you think of exponentially increasing. But to get that positive skew, we want an exponentially decreasing function. So here we have an exponentially decreasing function. And exponential functions can be described by a single parameter, which is kind of nice. It's called the rate parameter, or the symbol used for it is tau. And this value, it represents the mean of these data and also the rate of decay. So the rate parameter, just one parameter, will fully describe the exponential function. So we literally add these together and we get an exponential, sorry, an ex-Gaussian distribution function. And the way we describe this is with the mean and the standard deviation of the Gaussian distribution and by the rate parameter of the exponential function. So this isn't the mean of the ex-Gaussian, it's the mean of the Gaussian distribution. This is the standard deviation of the Gaussian distribution. And this is the rate parameter of the exponential function. But we use those to describe the ex-Gaussian distribution function. You're all looking at me like I'm crazy.
I know you from a long time.
He knows I'm crazy. So why did I create this specific ex-Gaussian distribution function? It's because when I asked MATLAB and I gave it the compatible trials, and I said, hey, tell me the parameters of an ex-Gaussian distribution function that match these data as close as possible, it spat out this result. And that's the data that I will be giving you in this study. So if you do the experiment, you'll have a bunch of reaction time. Then I'll ask MATLAB, hey, fit an ex-Gaussian distribution to it and tell us the parameters you found. And that is the data that I'll send you. I'll send you a mean, a standard deviation, and a rate parameter. A set of these for small white buttons and another set for the big yellow buttons. So to nicely show that this kind of fits these data, we can plot them on top of each other. So you can see it looks pretty good, right? So MATLAB uses some fancy math to create an ex-Gaussian distribution function with the 3 parameters that fit the histogram of the data that you give it. And then maybe oh, no, I thought I was going to overlay them, but I guess we do that later. So let's talk about these 3 parameters and what a change in them will look like in an ex-Gaussian distribution function. So we're going to go through those one at a time. So the black ex-Gaussian distribution function here, these are its parameters, and these are going to stay the same in our next 3 examples. And on each slide, we're going to focus on the change in one parameter shown in the red distribution function. And here you can see we're changing the mean. And what I did is I changed it by 20%, which you could change it by more, and it maybe would be even easier to see what changes. But a 20% change is, maybe the magnitude of what we might see in our experiment. So if the mean changes, remember, this is just the mean of the distribution of the Gaussian distribution, not the mean of the entire ex-Gaussian. But you can see what happens is the distribution kind of has a shift over to the right. So we've increased it by 20%. And if we look at the difference here, well, the peaks have moved over. And if it was a bigger change, like 40%, then we would expect a bigger change here. And if it were in the opposite direction, then the red distribution would move over in that direction. So a change in the mean kind of shifts the distribution left or right. Does that seem logical? Now, what happens if we change the standard deviation? So same parameters here, but now we're going to change the standard deviation, and we'll go with an increase every time just to keep it simple. So it's gotten larger by about 20%. So where we're going to see that change is to the left side of the distribution function. And because it gets bigger, you can imagine kind of stretching this out further. So if you think of the normal distribution, if we increase the standard deviation, it gets wider. And we're going to see that only the left side because the right side is more described by the rate parameter. So it gets bigger, so this gets pulled out. And the amount of area under this curve, the area under the curve, it has to stay the same. It has to add up to 100%, if you will. So if we stretch out the area of the shape, well, the peak has got to get lower. So that we have the same kind of total area underneath the curve in both cases. So increasing the standard deviation is going to pull the left tail out. And because this pulls out and there's going to be more area under that part of the curve, we need to decrease the peak so that the total area under both is still the same, or 100%. So we've got one more. Now we're going to have the rate parameter. And the rate parameter is similar to the standard deviation, but it's going to affect the right side of the distribution function. So let's make it bigger by about 20%. And you can see this tail. So you see the black tail, the original one with 110. And when it's 132, this tail is going to get longer. So we've increased the skew of our ex-Gaussian distribution function. So just imagine kind of pulling that side of the distribution function out. And because this is going to increase area, so we have to add in all of this area. Well, if we add in that area in here, we're going to have to subtract it from the peak. So the volume or the area of this should actually be the same as what we've added over on this side. Oh, there we go. Yeah, so the peak comes down. So do y'all have any questions about ex-Gaussian distribution functions, 3 parameters, before we go through another example.
Yeah, so the area of the curve, as you said, has to be the same.
Yes.
So that's essentially you're integrating the curve. What do you get when you integrate?
Well, I guess, yeah, as I was saying, I was thinking about, so that's going to depend on what your axes are. You know, so it wouldn't be,
If it's I see.
yeah, it wouldn't be 100% here, but it would be, I'm not even sure what to consider the area of this, you know, the millisecond density.
Sure, I got it. Is it easier to work with velocity?
Yes. So let's go through a full example of how you could apply this. So I don't know exactly what your data will look like. What I did instead is we're going to compare my compatible trials on the Simon task to my incompatible trials. So we've got 256 trials here, 256 here, which is a great number for doing a distribution analysis, more than we need. And we're going to fit an ex-Gaussian distribution to both of these, and MATLAB will tell us the parameters, and then we'll think about what those parameters mean. So I said, okay, MATLAB, fit an ex-Gaussian to both of these, and this is what we get. And let's see if we click between them. That, you know, it seems to, well, the graphs don't perfectly align, but MATLAB does a pretty good job of fitting these distribution functions. So the first one, it said, okay, well, the mean is 308, the standard deviation is 30.2, and the rate parameter is 110. This is the same one we saw previously. This is the new one. And we can see that the mean is larger, quite a bit different, as you would expect for incompatible trials. The standard deviation is larger, and then something I wasn't expecting is that the rate parameter is smaller. I thought maybe all 3 would be larger, but the rate parameter is smaller. I don't know if this is always the case for Simon or just my data, but we're just going to run with it as an example. So when I send you your data, I will send you the parameters for small white buttons versus large yellow buttons, and I will also send you the data so that you can make these probability density distribution functions as well. And I think one great way to show the difference between them, you know, here it's, when I look at these, it's like they look the same, right? But when you plot them on top of each other, then you can kind of see, oh, okay, well, obviously the red one is shifted. And so this is one way I would recommend to plot your data. So let's look at these 3 changes in turn. So this mean is larger, and we know when we increase the mean, we're going to shift the distribution. And we can see that the difference between these peaks. So we've shifted that one over. The other 2 get a little harder to compare because now we have multiple parameters that are changing and they're not right on top of each other like they were in our simplified example. But let's take a look at how we can compare these. So there we go. First one, easy. Okay, we've shifted the distribution over to the right. At the end, we'll say, what does that mean more in an applied sense to your reaction time? Standard deviation. So we increase the standard deviation. So imagine taking the left side of the black distribution and, you know, pulling it out this way. Now it's hard to see that here because this is also shifted over, so they're not right on top of each other anymore. But what you can do is you can find the midline of the black distribution. So I plotted a line down here, and then I measured how far does this go over, and it's, you know, that big. And then I found the midline of this function and measured how far does it go over. And what we would expect is that this is going to be bigger than this one because the standard deviation is larger. In other words, we pulled this red distribution out to the right. And the reason I'm measuring it that way is because the mean has also changed. So it's hard to see these things in combination. With a simple example, when the mean is the same, all we have to do is look, oh, well, this one's further out than that one. But in this second example, when they're not over top of each other, it's hard to see how do these tails compare. So I think this is a fairly good way to do that when there's multiple changes in your data. And I'm guessing in our experiment, we'll probably see multiple changes. I mean, I don't know, but it's likely to be complex because it's real world data. So now if I take the size of these two lines, and well, you can probably see the red one's larger, but it would be easier if I put them, side by side. And sure enough, you can see that the red one is larger. So if we think about this left tail has been pulled out further for the incompatible trials compared to the compatible trials. So it's a little harder to see because they don't start aligned, but that's one way to compare them. We can do the same. Now the other thing we should have seen here is because we pulled this tail over and the area or the volume needs to stay the same, the area should stay the same, we should see the peak decrease. Now we don't see that happening here because of the change in the rate parameter. In the rate parameter, we're going to see that the peak should increase, and those two things are canceling each other out. So rate parameter, it's smaller here. So instead of pulling out the red distribution, we're actually pushing it back in. There is a smaller skewed distribution in incompatible trials. That's a little difficult to see. You can see here, though, that even though the black one reaches its peak first, the red one starts to decay sooner. So already we have a hunch that the distribution is less skewed. But we can go ahead and use that same method as before to confirm that, yes, this has been squished in. That's the technical term. So we find the midpoint of this distribution. We measure how long it is to the curve. You could potentially do this at a higher or a lower point, but the lower we get, the more of the influence of the tail of the rate parameter. So if we did it way up here, this probably isn't going to work for us. We want to do it down here where the tail changes the most. Same thing when we looked at standard deviation. We wanted to look at that way down here and not up here. The red distribution, the distance from the middle to the edge, and they look quite similar, but if we line them up, you can see, yes, the rate parameter is smaller and that tail has been squished in smaller. Now, because we've decreased the area that way, the peak should increase to increase the area, and it doesn't, but that's because the changes in the standard deviation rate parameter actually almost perfectly cancel each other out. Here we're expecting to increase standard deviation, we expect it to decrease, and those largely cancel each other out, and there's very little change in the peak. So to kind of summarize all three together, well, what have we done? The distribution has shifted to the right. We have increased the size of the left tail, and the right tail, the decay in the skewness has actually decreased as we've gone from compatible to incompatible trials. So that's very descriptive, but how would I explain this in terms of reaction time? And I think it's best to interpret one parameter at a time. So if I were doing a distribution analysis, as you'll be doing in the last assignment, so we saw that the mean of the normal distribution function increased. So what I would say is that the reaction time of the majority of trials, so the ones within the normal distribution, were longer in incompatible conditions than compatible conditions. I'll move this down here. So when we look at incompatible conditions, the majority of trials, by majority I mean the normal distribution part, they get longer. So most trials are long. Now we can talk about the standard deviation of most trials, and with incompatible trials, the variability of the majority of trials was also increased. So when you do incompatible trials, your reaction time, most of your reaction times are longer and more variable. So that describes our first two parameters. Now we need to deal with the minority of trials that fall into that skewed distribution. And what I wasn't expecting here is that the rate parameter actually decreased. And that tells us that for the minority of trials with long reaction times, so referring to that tail, reaction time was shorter and less variable in the incompatible condition compared to the compatible condition. Why? I'm not entirely sure, but that describes what we're seeing in our distribution analysis. So the challenge for y'all, once you have your data, is to interpret the changes in these three parameters and relate it back to, well, how does the mean and standard deviation of the majority of trials change? And the rate parameter tells us about the mean and the standard deviation of the minority of the trials in that tail. Yes, Keith.
I have two questions. So the first one is the rate parameter, because it's getting smaller, we're getting a closer curve to a normal distribution.
Yes.
Okay.
If-
Second,
Yeah, if your rate parameter was 0, then it would be perfectly normal.
No, okay. And the second question is, why are we not using mode? Since we're talking about the frequency of, I guess, the highest amount of values in that midpoint, right?
Sure.
We're not using mode, and we're using mean to describe the curve.
I'm not entirely sure. We don't often like to use mode. On these curves, I guess it would work out well, you know, it would be that top value, right? I have an argument for why we don't use median, but maybe why we don't use mode is because if we look at the underlying data, the mode for it may or may not be at the peak of the distribution, you know, in these data, because the mode here would change based on how small you make these bins. But you're right, I think the mode would be appropriate once you have the distribution function, but it's not something I see used. And I don't have a good answer for why. So the assignment is to analyze your own data or someone's de-identified data. So you don't need to worry about waiting for everyone to do the experiment. You can do this on your own data. The question, the problem we're trying to solve is which button is more accurate. And instead of just relying on mean reaction time, we're going to answer that question by looking at, you know, all three parameters. Distribution analysis. So you'll want to explain the differences in your distribution functions. So you'll get a distribution function for the small white buttons and for the large yellow buttons. And the challenge is to say, well, what's different about them? What does that tell us about reaction time, and which button is then more accurate? You do not need to explain what an ex-Gaussian distribution function is. We can just assume we have that knowledge. So you don't need to say, oh, ex-Gaussian is made up of a Gaussian and an exponential. No, just skip all that. Let's dive into kind of answering the question and performing the distribution analysis. Oh, I will send you your parameters. So the three parameters for each set of buttons. And I will also send you data so that you can make those distribution function plots. So what I need from you is, if you want to volunteer for the experiment, to email me and we can set up a time. Thankfully, there are 5 of us on the research team. So if I'm not available, someone else on the team can test you. But it is going to be an official test session where you come in with a member of the research team. The research team is definitely available in the afternoon and some mornings. So if afternoons work for you, that's great. And what you can do when you email me, if you're going to volunteer, is just let me know sometimes that work for you. And probably within those times, I can find someone on the research team that fits with. So our schedule here, we don't need to do a lab demo because you'll come in and you'll be walked through the experiment. So data collection is due next Wednesday, if you are going to volunteer for the experiment. And then your presentations will be the Wednesday after that. And then we don't have anything after that point. The only potential issue is, say we have a snow day or something weird on this day, then we would have to reschedule presentations. But we should, if everything goes well, be done this course on the 17th. which is before Thanksgiving, right? After Canadian Thanksgiving, before US Thanksgiving. Does anyone celebrate Canadian Thanksgiving?
When is that? Usually in October, right?
It's in October, yeah.
It's over.
It is. Guy, when is Brazilian Thanksgiving?
We don't have it. Yeah, we're thankful, yeah.
Hold on, did you not massacre all your native population?
No, well, we did.
Oh, there
We
you
just
go.
don't celebrate it.
Yeah. Maybe.
Yeah.
But if you have any other questions, feel free to stick around. Otherwise, I will likely see you on the lab. Or a member of the research team will see you.
I'm always there.
So I'm going to stop this video.